Hello, I'm Caskey. I'm here today because I build monitoring systems, and basically I've seen the same problems being solved over and over again as people try and cobble together solutions for monitoring modern services. And what frustrates me is that while we have really good models for today for administering large fleets of machines, we have really good models for building web services if you're a developer, monitoring seems to still be stuck in what I call the 90s, okay? I'm sure the other people call it the 90s as well. But, and I see many people basically reinventing the exact same wheel, using similar parts over and over and over again. And I have no problem with people reinventing the wheel, but it'd be nice if we at least had kind of interchangeable parts. So I'm going to talk about a model that we use at Google for evaluating monitoring systems. And when we decide to address monitoring issues, having a formal model is useful because it lets us say, you know what, we know that these are the problems that are going to come up, and so any solution before we build it needs to solve these problems. Okay? So let's flip through it. I've got a ton of slides. Many of them are referenced. You guys can look at them. They'll be shared. And this is going to be interesting. Would you like to go and like disable some stuff here, so we don't like get an unfortunate window into your life, or a window into your unfortunate life? That kind of sounds bad. Oh my God! Actually, I just realized they're recording this. So my usual plan is to swear everybody in the room to secrecy, that they won't tell what I said while I was talking, but. Oh, that's even better than the, okay. All right, so no more excitement. All right, so, oh, I can adjust the volume too. Sorry, I've been given way too much technology than I can handle at this point. All right, metrics. This was a great quote that I came across. It turns out that a number of scientists got together in the 40s when there was kind of an evolution in science and moving toward objective, repeatable, not just repeatable measure, but what does it mean to actually measure something? And so I found this quote, and I've kind of stuck it on a Post-it note for a while, and it's basically, it's a nice way of saying, you know, what is it that you're trying to do when you gather a metric, right? Or when you monitor something. And so I threw it in there because it's kind of nice. The assignment of numerals to things is so as to represent facts and conventions about them. I mean, it's nice when somebody's talking about disk reads or I/O per second or something, that we at least are speaking a common language, right? So why am I here presenting a theory of monitoring? Well, many people are building monitoring systems. It seems like monitoring's easy. In fact, I still run into this on a regular basis, even within Google. Someone's like, oh, I just need to do some monitoring, right? But it turns out that monitoring is deceptively hard. It is actually very, very hard to build a useful monitoring system, especially in modern systems where they get very, very big. So I tried to come up with a model that we, 3 years ago, that we could use, that where then say, all right, why is it that monitoring fails? What are the problems that keep repeating? Okay? And I tried to validate that model by going and looking at other systems that try and do monitoring and make sure that do the problems that they have fit in where there are holes in this model and how it maps to their solution. So what do we monitor? This is just very basic background stuff in case you have no idea what monitoring is. Essentially, we have named values with timestamps, and there are various attributes. Obviously, the I/O per second on this drive is different than the I per second on that drive, and so we have to capture all of this meaning in order to then analyze it later on. Here, I think I'm using an example of a web request that happens to be, yeah, this is just a counter for how many 200 responses are coming out of a particular web server serving a particular vhost at some point in time, right? I work for a web company, so a lot of stuff's going to be web-related. And when I say QPS, in case I slip into that, that's just our notion of requests per second, our concept of a load, queries per second. So basically, it's a named value at some time, right? I'm going to keep touching that volume button, aren't I? So when we decide to do monitoring, though, there's the issue of what are you capturing? Not what, I'm sorry. What you're capturing is that. How are you capturing it? It's one thing to say, oh, right now at this moment, we are doing, you know, 200 IOs per second, 50 disk seeks per second, and so on. But that is of different meaning to different people based upon how often you're gathering that value. Different people need it at different rates. An operations engineer, a DevOps person, someone who's on call, needs that data much more quickly than someone who's just trying to look at a report at the end of the quarter to see how many 30-day active users you've had over the past 90 days, right? So there's latency, and then there's diversity. Diversity is what's really the nasty bit, because as we move into virtual hosting, sorry, I'm getting louder. As we move into virtual hosting, what used to be done with one big server with everything kind of packed into it as best we could because bare metal was expensive, now we take the same bare metal and we pack 10, 15 virtual hosts onto it. But now we have 10, 15, 20 different metrics, time series, that are measuring each of their individual performances. We have better visibility into what they're doing, but we then have more data about that. So how many different metrics are you collecting? It used to be that you'd get away with calculating I/O load, network busyness, CPU activity, and you'd be fine. Handful of metrics. Nowadays, it's not uncommon to capture thousands of different metrics. If you have 100 machines and you're only capturing 10 metrics on each, you're still capturing 1,000 metrics, right? And that's 1,000 different time series. And if you want high resolution data about that, you're capturing it very, very rapidly. You're building up a lot of data. As a PDF, this is going to be animated and everything. This is going to be so cool. Never mind. All right, so pretend this is like a really dynamic slide with like the arrows moving and all sorts of stuff. But when I was looking at those three attributes, the resolution, latency, and diversity, I was like, okay, how do those change and who needs them at with different types of values? Operational health and response needs high resolution, low latency, and high diversity. They need all the metrics from everywhere, and they need them right now. Right? It doesn't do any good to find out at the end of the quarter that, by the way, 6 weeks in, you had a disk that completely imploded because something went horribly wrong, or a bad software push broke it, right? You need to know, ideally, as the software push is rolling out so you can roll it back. Then you have what I call quality assurance, and this is a very confusing area. So high resolution, low latency, high diversity. That's the hardest case, operational health and response, right? Then what happens if you increase the latency? Who could benefit from high resolution, high diversity metrics that aren't really immediate? And this is where what I call the QA, SLA type metric. A developer who is looking into performance problems, a stack trace or a D trace or a performance or a P trace or some other performance dump is as good to them offline as it is online. Well, it may be a little bit better to do it live, but if you're working in production systems, it's very common that your developers do not have direct access to the production system, so you have to provide them with metrics so they can see what was going on at the time. And so you drop latency and you have this use case of quality assurance and also SLA calculation. If you have SLAs or SLIs and SLOs and you're trying to compute how they are, you generally aren't concerned right away about them being computed. Then there's capacity planning. This is a case where you don't really need to do capacity planning on a minute-by-minute basis because the fact is the lead times for provisioning are often longer. Now, there is a lot of really cool stuff being done with dynamic scaling of infrastructure with virtual hosting where you can spin up new instances as load comes in. That changes that metric. That changes the concept a bit, but it's still lower resolution than real-time monitoring for alert response. And then you got product management, and here, screen's on here. Okay, then you have product management, which is those things like the 30-day actives, 7-day actives, looking at the long-term trends of the product. And essentially, resolution's going down, latency's going up, and diversity is going down as well. And so when I labeled those, I was like, wait, this is only 4 of these use cases, 4 possible combinations. Do the other combinations mean anything? And I was like, okay, where you have low resolution, but low latency and low diversity, and I was like, that doesn't really seem to make sense. And I realized load balancers do exactly that. They have 1, maybe 2, maybe 3 metrics that they use to decide where they're going to shift load. It's low resolution, low diversity, but very low latency as well. So anyway, I haven't figured out the other 3. I want to have a discussion about this. Find me, seek me out, and I want to figure out, are those other 3 just a nonsensical combination, or do they actually mean something? So, monitoring at scale. This is a quick thought exercise which shows why monitoring is a big data problem. So typical web server, if you only have 25 metrics in your server, and you got a web server and a database, who has this simple of a system? Anyone? No? No. I think, what? No. So yeah, no one does, right? The reality is that things get very complicated very quickly. If you have 100 million active users, the math for this is at the end of the slides, and for typical web service, you could easily have 200,000 peak QPS. Again, that's requests per second for your API or whatever. If you have that, you pretty much need to deploy your service like this, right? You need to scale out horizontally. You very quickly will end up with 10,000 servers, which means you have 25,000 individual time series. Now, in an operational response situation, you're looking at 166 metrics per second. Not that bad, but very rarely is there just a two-layer app that's being deployed at that scale. Instead, it's a hierarchy of many, many, many components. You might have a storage layer at the very bottom, but you have other cooperating components, authentication layers, and so on. And so you can end up with 12 different kinds of servers. You're now at 3 million different time series. That's 10,000 metrics per second that you have to gather and analyze. All right? Now you need regional diversity, N+2 capacity, and now you're at 4 million metrics, 13,000 metrics per second, right? That's not a small problem. And of course, your monitoring system has to be able to reliably traverse those unreliable intercontinental links, which is its own problem. So you're looking at 10,000 metrics per second, and every single time you gather them, a full sweep, 32 megabytes of data, right? Now, this 10,000 metrics per second, that's been at 5-minute resolution. Now, 5-minute resolution is okay, but we prefer to, the minimum really is 1 minute. If you're doing 1 minute, you're not talking about 10,000 metrics per second, you're talking about 50,000 metrics per second. You're gathering half a terabyte of data every day. If you want to plot a graph of the last 30 days, you got to scan through 15 terabytes of data. Monitoring is a big data problem. No longer is it just you have a monitoring host and you have it scrape some values. For a real app, you need big data solutions, right? And I feel like this is why, as we try and build monitoring solutions, it feels like we're never quite getting there. We can't solve this problem. Why is it that it seems so intractable? Well, it's because we're looking at it the wrong way. So what do we monitor? Name, timestamp values, high resolution, large quantities of data. There are different consumers of that data. There's no reason that we need to have separate pipelines for reporting data for customer A versus customer B and customer C and so on, because you need the same kind of thing. And of course, reliability. So this is the model. This is the good part. How am I doing on time? I'm good? Okay. So this is the model, all right? The what's and the whys were back there. This is the how. If you're going to build a monitoring system, it's my assertion, and it's assertion I want you to challenge because I think, and in fact, I know there's problems with this model. In fact, just yesterday I was discussing it, and it turns out that there might be some issues right around the middle part near the bottom, right? There are 7 parts to monitoring. You have to have a sensing component. You have to gather and count and increment counters. You have to bring those counters together from many, many diverse systems. You have to then do computations on that. It could be as simple as thresholding. It could be dynamic moving time series analysis. It could be who knows what. It could be autocorrelation. You have to then deal with alerting and escalation. Hopefully then you have some sort of incident management system you can hand that off to. And then of course visualization. Visualization is a huge category, right? Now you also need, of course, there's those 2 cross-cutting concerns of storage, right? But then there's the real kicker, configuration management, right? If your monitoring system requires every monitored node for someone to go in and manually set up what metrics they want to capture at that node and forward it to another one, you're not going to be able to manage 10,000 servers, right? You need to be able to centralize your configuration management. And so that's the last comer to the game lately as you look at the evolution of monitoring systems from MRTG and Nagios back in the 90s to what we have today. The final piece that's kind of dropped in where people realize, wait, no, we really need to be able to solve this, has been configuration management. And when you look at the history of monitoring systems and what people are solving, that's been the latest one. This is just in more detail about each of these. What is sensing? It's just trying to identify a specific value. Is it a CPU counter? You need to instrument your binaries, all right? You need servers that are providing metrics that you can look at, right? If a server's not actually generating a number that says how many processes are blocked waiting on a lock or some other element, then you can't really do anything. The game's over, right? But many different systems have different ways of doing sensing. Who here uses Nagios plugins for something? Right? Yeah, for the video, almost everybody. Yeah, Nagios plugins are one of the beautiful things that came along. We're now 15 plus years after Nagios, way more than that. And even new monitoring systems reuse them because it's such a simple interface. It's got problems, right? But it's a simple interface and it's pluggable, and so it solves this as a dynamic reusable component, okay? So that's the sensing problem. Storage. Storage is a real nightmare. It's not enough to simply name a value and write it down because values are more complex than just a single named value. If you're only on one machine and you're counting I/O per second, the context is implicit. It's this machine. But when you're gathering data from 1,000, 10,000 machines, and you're measuring network usage, throughput, and so on, you need to know, well, which machine does that apply to, and which process on that machine am I counting that? So no longer is it just a single named value. And you'll end up playing games with dotted notation to try and pack metadata into the name of the variable. You need a storage layer that supports, as a first order member, the information about where that data came from and what it means, okay? And so, collection. This is the problem of getting all that data into one place or in several places. This can be a difficult problem if you have a distributed environment. If you are on multiple continents, having reliable collection can be a problem. And of course, as I was mentioning, the storage layer, assuming your storage layer can actually retain the fidelity of where those metrics came from, your collection layer also needs to be able to understand that the identity of those metrics needs to be preserved along the way as it's being aggregated, collected, and brought down. And there are many different solutions to the collection problem. Analysis. This is how are you going to make computations about that data? How are you going to reason about it? How hard is it for you to say, you know what? At this time, I'm really curious as to how my incoming requests per second relates to my I/O load on a per server basis. And I want to be able to make assertions that, okay, the ratio relationship between those two should have some particular bounds. And if they're not, I want to be able to set an alarm off, right? Setting an alarm off is basically any kind of anomaly detection. There's a lot of interesting work on anomaly detection in the IDS realm. If you aren't reading the research in intrusion detection and in threat analysis, this is where a lot of the interesting stuff's going on. Unfortunately, most of the models work on very small data sets, and I always get a little sad when I'm reading one of the papers and like, okay, we did this and we were able to do distributed threat analysis, and we worked with 12 metrics per machine. It's like, so close. Because this is very computationally intensive. The fact is, simply analyzing that 50,000 metrics per second is a computationally complex problem. You cannot do N by M analysis, comparing every metric to every other metric, looking for anomalies in real time without some pretty serious computing hardware. It'd be a waste of time to try and compare 50,000 times. Actually, it's not. Remember, that's 50,000 per second. That was out of 4 million unique time series. You cannot compare 4 million time series to every other time series and look for anomalies. So how do you solve that? This is its own application. It's its own problem. It's complex. And then, of course, escalation is about getting that notice out. And, of course, this never happens late at night or early in the morning. So don't do that. A lot of people like to leave this part of their monitoring system out. We'll look at it in the morning, send an email. Never monitor by email, by the way. All right, visualization. Visualization is critically important. There are many problems that if you look at it, if you look at the right visualization, the problem becomes immediately apparent. However, if you look at a giant table of numbers, who knows what's in there, right? I mean, you could show me in postage stamp size 100 graphs, and it would be very easy for any of us to see 2 of them suddenly spiked at the same time. It's trivial. The right visualization is worth its weight in gold. That's a bad visualization. Well, actually, it's not that bad of a visualization. Clearly, you can see relationships among some of the data there. Anyone know what that is? No? That's not a spreadsheet, but that was a good guess. Well, I guess it might be, but I mean, what is the data represent? Okay, that's cool. If somebody does figure it out, the prize for them. No image search. So anyway, yeah, but we are still human, and so it's hard to go beyond 3 dimensions of data presentation. Heat maps are a wonderful thing. Use them. This uses color and space, and actually, if you were able to zoom all the way in, you'd actually see there are numbers written in there as well. I think this ends up, I counted up, I think this was a 5 or 6 dimension plot if you look at it. Of course, if you don't know what you're reading, and I didn't know what I was reading, I was trying to find out the cardinality of that graph. It's kind of confusing. But very often your visualizations are goal-oriented. Visualizations, and this is a little bit of an aside, need to be actionable. Showing someone a graph that they can't do anything with or doesn't convey any meaning is kind of a waste of their time. You may as well show them a table of data and say, well, ignore it at your leisure. This is one of my biggest pet peeves, so I'm taking an entire slide here to talk about it. Disk usage in a pie chart. It drives me nuts, because this is completely useless. Like, okay, what are you going to do with that information that you couldn't do by just saying 40%? Certainly nothing. It's like, all you can say is my disk full? No. Thank you. So, disk usage is one of those great examples of without analysis, it's useless. You need to get the first derivative of disk usage. What you care about is, will my disk be full in 1 day, 2 days, 5 days, 10 days, 30 days? Are you doing capacity planning? Do you need to look at your storage across your entire cluster? Are you doing an incident response? Is my disk at 90% right now? No problem. I have many systems where they're at 90%, and they fluctuate between 80% and 95%. That's the healthy range of the system. This is just as useless as showing a pie chart for CPU utilization. Right? It's a resource, but what matters is the evolution of it over time. So also, it's impossible to see, but the example on the right is showing a system that only can break down under a fixed taxonomy, a fixed hierarchy of devices, nodes, and eventually you end up at a metric, but there's no way to look at it across. You can look at any individual host, any individual component, but you can't actually look at, okay, what is my total I/O throughput right now across my entire fleet? Am I using 6 terabytes per second, or am I using 6 gigabytes per second of my disk bandwidth? And so this particular system can't visualize anything other than at the single host level. So push back if anyone says, no, these are great visualizations. No. Avoid pie charts. And pie charts are just bad in general. Unless they're a picture of Pac-Man, then they're good. All right, configuration. Now this is, did I do that? I'm sorry. All right, I won't touch myself. Wow. Okay, this is going real well. Remember that oath of secrecy? You're all sworn in. Okay, so configuration management. This is the real, it's hard. Thankfully today, for just system provisioning, we've got a lot of great tools. In the past 5-10 years, we've got Puppet, CF Engine, Chef, and so on that have really made our lives easier for deploying big systems, right? Anyone, it's no longer the day of Kickstart or having to carry. I used to carry a floppy around from machine to machine. I'd use Pixie to boot my kernel, and everything was all over the network, but I had to put the floppy in to set up what was going on in the system. Okay, yes, I built bad systems, but don't hold that against me. So when you have a distributed system, you need to have effective configuration management. All right? You need to be able to, in a centralized way, say, you know what? Here's all the stuff I want to gather. If I'm making a change to what metrics I'm gathering or how frequently I'm gathering, that should be a single point change that you can then reliably push out to your entire fleet. Right? You need to have effective tools for managing your configuration and also doing things like, you know what? That was a really bad config. I need to roll that back. You need to have release and controls over your monitoring configuration just as you do over your production systems configuration, right? So as we said, these are 4 of the goals that we're trying to accomplish, and those are the 7 boxes that if you can fill each of them in a way that meets your needs in those, then you might be pretty well on your way. So starting at the bottom, I tried to say, which of these boxes are most important for which purposes? Product management is the easiest, and so I started there. Always start with the easiest problems. And product management is mostly focused with looking at long-term trends. And so storage is going to be important, obviously, because you got to keep that long-term data. You're going to do a lot of synthesized metrics. No manager cares about how many requests per second or how many bytes per second are going in and out of your disks. What they care about is how many users are using what features and so on, click-through rates, conversions, and whatnot. And of course, they want nice, pretty graphs. You also want nice, pretty graphs. But when you're doing product management or even fleet management, which is a little bit more like the next slide, you really are focused on analysis and visualization, all right? Capacity planning. We all do capacity planning. The only real difference between that and product management is there's a bit more metrics. They're a bit more lower term. They might be slightly less processed because really you'd only need to find out how fast you're using your disks to figure out if you need more disks, or you need to go and stop things that are writing to disk. There are some proxy metrics. These are representations or values that say, am I going to need more capacity in the future? And of course, you need some alerting, which indicates when you're approaching some threshold. I don't want to have to go and check, do I have enough disk space every week? Instead, it'd be nice if something said, oh, by the way, in 60 days, you are going to be at your high water mark for your acceptable free disk space. It's time to buy more disks, right? Or it's time to do whatever you do to free up disk space. Capacity planning is an important part of the process. And the most important aspects are visualization and so on. Quality assurance, as you may notice, we're filling in more and more of these boxes being green. And just to skip ahead, operational response, pretty much everything's important for operational response. That's the hard case. Now, if you can solve this case, you get this, and you get this pretty much for free. So most of my work is focusing on solving this case just because that's my job. And if I can solve that, the other ones, you don't need really add anything else. This is the hard case because you have everything to its extreme. You need high resolution, high diversity, and low latency, okay? And of course, you're storing a lot of data. So I'm about to go into, this is a big apology, so the goal is not to offend anyone. One of these slides here, I found out there's a maintainer of one of the products, and I'm not trying to criticize these products. I'm just trying to say, if you have this system, here's where I see it as having addressed these layers of the system, of the model, and here's where it may be lacking, okay? Now I'm going to start with the oldest two systems out there because when you draw a family tree of all the monitoring systems out there, they can usually be brought back to one of two systems that were developed in the 90s. Skip over that. Okay, MRTG, all right? A venerable old monitoring system. It basically addressed the sensing part by simply scraping SNMP, and it addressed the storage part. It used RRD. Well, it didn't always use RRD. You now can use RRD, I think. And of course, it provided visualizations. I mean, this is, for many people, this was like, oh, wow, I get graphs of what's going on. This was great because it was the first kind of big step that was widely used that went beyond something like this, SAR, TOP. These are very useful diagnostic tools, very good tactical tools, but not very good strategic tools. This gave us a strategic tool that could say, you know what, I want to look at how my bandwidth trend is looking over the last 6 months, last year. You can pull up the graphs. It's great. And it was a good first step. And it is the grandfather of many, many, many monitoring systems. And in fact, if you flip back and forth between some of my slides, you can squint and you're like, hey, is that MRTG I'm looking at? No, it's something that was developed 10 years later. So it's great for examining what's going on. Clearly something interesting. Do I have a laser? Ha ha ha. I'm not that excited by lasers. Pew, 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 pew. Clearly something interesting happened right there and so on. And so you can actually get some useful operational data about that, right? But of course it doesn't have alerting, and that's really important if you want to do real operational response. This was useful for net admins who were just, they're basically sitting there checking their graphs every day. Nagios was kind of it made a big splash, and many people still use Nagios. Who here has used Nagios in the past? All right, 100%. Who here still has Nagios somewhere in their environment? Wow, that's awesome. Who here wishes Nagios could do a bit more, be a little bit easier to manage? Yeah, me too. I love Nagios. I mean, when I discovered it, I was like, oh my God, why haven't I been using this forever? Well, it didn't exist forever, but why didn't it exist forever? Because it added alerting. I could actually be notified. I didn't have to go and check to make sure everything was okay. I'd be told things weren't okay. All right? And what it allowed is it added alerting and escalation, which MRTG had no accommodation for, right? And it had sensing. It had a little bit of collection, but the model of Nagios has its shortcomings, as we all know, right? The collection is a little bit weak. And of course, who loves editing Nagios configuration files? Yeah, you freak. Yeah, Nagios is not fun, right? But now, as you can see, though, why is Nagios better? My assertion is that it's better because it does a better job of these elements that we need, right? Now, moving forward, Ganglia. Ganglia is now 12 years old, I think. It's old, but it's currently the best solution. Volume. It's one of the better solutions for distributed metric gathering. It does that collection process, right? It's a nice combination of multicast at the local level, direct scraping at the aggregation level, and you can chain together aggregators and so on. And so what it really does is it addresses that second box, collection, bringing those metrics together, because no longer was the Nagios model of going out and talking to every single system acceptable. When you have even 100 systems, Nagios begins to be a little bit shaky. Well, it does better now. If you throw enough iron at something, you could get stuff done, right? But Ganglia solves a critical problem, a critical deficiency in Nagios. But it drops out a couple of other important elements, namely alerting. It's got support for analysis. You can plug in your own analysis and so on. It's a great building block. And many people have taken Ganglia and attached to Nagios. Who has Ganglia feeding into Nagios? Yeah. The fact that there's more than one hand raised here shows that you guys are finding the exact same problems. You need collection and you need alerting, so let's take something that does collection and glue it into something that does alerting, right? So now Ganglia, when you look at its front end, I mean, the front end is nice and all, but it looks a lot like MRTG, doesn't it? Yeah, because the heritage of Ganglia, when I draw the family tree, Ganglia is kind of a derivative of MRTG. Even though most people hook it up to Nagios, because what it's missing is the alerting. Cacti. Cacti is great. It tries to solve one of the biggest problems with MRTG is that MRTG was a very monolithic, flat data model of what it was monitoring. Okay? Cacti creates structure around that. Okay? It essentially wraps up MRTG. Says, all right, you need to be able to manage many different types of sets of MRTG graphs. And it tries to create structure. It's great. It addresses, it builds upon what MRTG did and adds a bit more ease of configuration management. But it doesn't really solve all of the problems, yet it was better than what you had before. You're better off with Cacti than MRTG. If you had to pick between the two, go with the one. Of course, Ganglia plus Nagios is still very popular. But when you look at the visualization, it's not as sophisticated as modern visualization tools. We'll get to those later. What's my time? Oh, wow, okay. So anyway, Sensu, it does collection and distribution, and it has a plug-in mechanism for, you can pretty much put any data you want in at the beginning and run processes at the end. It's very useful. Then we have Logstash. Logstash is focused heavily on collection and storage, but it's missing a few other things. We got to put some other visualization front end on it. In fact, I believe they recommend, in fact, even their search engine, they use Elasticsearch. I mean, we're getting into modern systems here where they're actually combining useful general purpose open source products to make something great. OpenTSDB, this here is the only thing that I found that is purely a single point solution to one of the aspects. The goal of, the purpose of OpenTSDB is just to solve the storage problem of metrics. All right? It uses a completely different data model than many of the others. It's the first break from the MRTG RD tool model, and it actually adds in labels here. Now, this is a very simple example. A proper monitoring system would have a dozen labels or more going off the end, right? But at this point, you now have a storage layer that can capture all the fidelity that you need for a full monitoring system. But of course, we're missing the other 6 boxes. But starting at the bottom up, we've gotten some great tools that are beginning to solve the problems that are purely UI related. Visualization. D3.js, great way of exploring data, right? It creates dynamic interaction. Who uses D3 for monitoring? Or who uses D3 for anything? Yeah, when you play, it's awesome what it produces, right? And I'm hoping someone will find a really cool way of plugging that into a monitoring system because it creates dynamic, interactive, being able to explore a data set to figure out root causes via D3 would be really awesome. You could build a very powerful tool. But it's just visualization. Graphite, and this is huge. Who's graphite? Yeah. Graphite solves the visualization problem very, very well. All right? However, the Carbon Whisper and the RRD tool heritage don't address the big data problem. But you produce great graphs. People love graphite. I think it's an awesome tool. It's certainly a big step up from, well, you remember the MRTG graphs, right? Would you rather have this or MRTG? Obviously this, right? But its focus is primarily around the visualization layer. And so everyone out there is gluing these pieces together. In fact, who uses Ganglia plus Nagios with graphite? Couple? 1, 2, 3, 4, yeah. Because Nagios' visualization sucks. Now, Nagios has its own problem that it takes a very binary view of up versus down. And then there's Shinken. Shinken actually takes Nagios plus graphite, throws in a configuration management layer to try and provide a complete solution, right? And this is the newest of all of them. And now, just because it's all green doesn't mean I endorse it. I'm just saying that it specifically addressed each of those areas. And so it's a complete solution that deals with distributed collection, bring all that data together. Unfortunately, it's Nagios based, but they did slap graphite on the front of it, which makes it much prettier. And then, of course, cloud monitoring. This list, which is, I think there's 17 of them, I took 5 minutes and just looked up cloud monitoring. There are many cloud monitoring providers out there. They provide the whole stack. If you can get it with cloud monitoring, then good. But it's a very complex thing. It's software as a service. Many of them are based on some of these open source products. And then finally, in the real world, Nagios, Graphite, Sensu plus Logly, and throw in some Ganglia. We lack interoperability. We need better tools. If we can come up with common interfaces for these, we can have a mix and match approach that isn't a nightmare to configure. And you can decide today, I'm going to use Graphite, tomorrow I'm going to use D3. Decide today I'm going to use Nagios plugins to gather my data, or I'm going to use Nagios plus Ganglia. Nagios plugins feeding into a Ganglia pipeline, which I then use Sensu for dispatching analysis and alerting, and then it feeds into who knows what. So. I did Logstash. There is Logly as well. Those are two different products. Yeah, Logly and Logstash. Where's Logly? Oh, did I? I apologize. That was a typo. I meant Logstash. I'm sorry. Thank you for calling me out. No, I totally meant Logstash. Yeah, so Nagios, Graphite, Sensu, Logstash. Not that Logly's bad, if anyone hears from Logly, right? So anyway, you build a pipeline. These pieces can be fit together, but it's a very manual, painful process. If we can come up with conventions that make it easier to do that, we'll all have better monitoring, and of course, we'll all be happy. And we'll all, pagers are silent and systems run. So yeah, thank you.
Thanks, Caskey. We have time for 1 or 2 questions. From the back. All right. Okay, could you repeat the question?
Yeah, he mentions Collect D. Yeah, I gave this talk 2 other times as kind of dry run to our local LOPSA chapter, and yes, each time there are many, many solutions to this problem, and I don't mean to omit any really valuable ones. There are many. There's SenseD. So I was trying to just pick some highlights that I came across, representative examples. There are many, many other solutions. But when you look at them, it's my hope that you can say, you know what? How well does this address, and what part of the stack is this solving? And therefore, where am I missing important elements? No? All right.
All right, I guess I yell. Have you looked at Zymon at all?
Yes, briefly.
Okay.
Yeah, no, yeah.
Everybody
again.
I've shown it to has dropped Nagios and never gone back.
Yeah.
It's basically Nagios twice the functionality for half the work.
Yeah, and there are many great, better versions of this. So yes, I am happy to receive long lists of other better solutions than what I've shown. Again, these are representative examples showing that the problem is common to that the solutions fit into various patterns. So yes. So.
One more.
Okay, one more.
From a very high level, how did you guys solve the problem with random
I can't really answer that. I'm sorry. I mean, I'd like to, but there's limits on what I can talk about. And so we have solutions for the random I/O problem. Yeah. And I certainly wouldn't say they're good solutions. There are better solutions out there, and I suspect someone probably in this room has a better solution for solving it. But it is a difficult part of the monitoring because it is a lot of data. Monitoring is a big data problem. If there's any takeaway, that should be it. Okay. All right. Thank you so
Thanks,
much, everybody.
Caskey.
And if you see me, fight with me. Tell me I'm wrong, and tell me more monitoring systems I forgot.
Thank you very much, Caskey.